In this explainer, we're doing something a little different. We're going to fuse 4 pretty dense research papers into a single cohesive framework to really understand the past, the present, and maybe even the future of artificial intelligence.
It really does feel like a paradox, doesn't it? On the one hand, you see these absolutely breathtaking advances in AI every day. But on the other, you hear all these experts talking about the harsh reality of diminishing returns. So how do you square that? To make any sense of it, we need to get past the headlines and find a more structured way to think about the problem.
So here's the big idea we're going to unpack today. AI progress isn't just this random, chaotic explosion. It's a phenomenon that's actually playing out across 4 distinct but totally interconnected layers. From the absolute laws of what's even computable, all the way down to the actual silicon chips that power our models.
Okay, let's dive right in. We're going to start at the very top. Layer 1, uncomputability. This is the big one, the absolute limit. The fundamental boundary of what any computation today or 1,000 years from now can possibly achieve.
Now, to get our heads around these super abstract limits, we have to go back to Alan Turing and his idea of an oracle machine. Just think of it like this. You have a regular computer, but it has this one special magic button. And that button, the oracle, can instantly solve one problem that's completely impossible for the computer to solve on its own. It's a brilliant way of asking, okay, what could we compute if only we could solve this one really hard thing?
And this is where things get really interesting, because it leads to this pretty profound idea. The moment we figure out how to automate a task, turn it into a set of rules a machine can follow, a whole new, higher-level problem just pops up. The challenge of actually managing and guiding the very process we just created. It's a never-ending cycle.
This cycle actually has a name, step mechanization. And what you're seeing right here is basically that endless climb, visualized. We solve one set of problems, which just creates a new frontier of unsolved problems, and the whole cycle just repeats, on and on.
Okay, so what's really cool about this is how it formalizes that loop. You start at a given stage, defined by whatever your current oracle can do. Now that stage has a hard limit, a set of problems it just cannot solve. Progress happens when you take a step, mechanizing a problem just shy of that limit. And here's the kicker, in doing so you've created a new, more powerful stage, which, you guessed it, has its own new hard limit.
So the crucial point, the big takeaway from this deepest theoretical level, is that intelligence isn't some finish line you can cross. It's not a final destination, a problem that gets solved. It's the process itself. It's the act of climbing this infinite ladder.
And that brings us perfectly to Layer 2, feasibility. Now we're zooming in. We're moving from what's possible in principle, with infinite time, to what's actually possible in practice, here in the real world, where time is a resource we don't have enough of.
This brings us right to the doorstep of one of the biggest, most famous unsolved questions in all of computer science, P versus NP. In simple terms, it's asking this. If you can check the answer to a problem really quickly, does that mean you can also find the answer really quickly? It's like a Sudoku puzzle. Checking a finished grid to see if it's correct, that's super easy. But actually solving a hard one from scratch, that can be brutally difficult.
But instead of seeing P versus NP as the single massive wall, we can think of progress as climbing a ladder called the polynomial hierarchy. Each rung represents a more complex but still feasible type of problem. We start with stuff we can solve directly. Then we move up to things we can verify. Then we get to problems where we can handle a whole back-and-forth game of proposal and challenge to check the answer.
Now, the key takeaway here isn't that AI is going to magically solve NP-complete problems and break all of cryptography tomorrow. No. The point is that we can understand AI's progress as a steady climb up this ladder, widening the scope of what we can actually achieve in a reasonable, or polynomial, amount of time.
Okay, so we've got our theoretical guardrails in place. Now let's look at Layer 3, scaling and efficiency. This is the engine. This is what's actually driving the incredible progress we're all seeing today.
To really get a handle on scaling, we have to make a really crucial distinction. There's something called logical compute. That's the abstract mathematical amount of work a model needs to do. Think of it like the recipe. Then there's the physical hardware that actually does the work. That's the oven. The scaling laws are all about the recipe. And this right here is the answer to the paradox we started with. Yes, if you look at the scaling laws, they absolutely show diminishing returns. You have to pour in more and more logical compute for every little bit of improvement. But, and this is the key, we keep getting dramatically, unbelievably better at converting our physical resources, like electricity and silicon, into that logical compute.
It's this hidden efficiency from better algorithms, better software, and smarter hardware that keeps the progress going.
And this chart just brilliantly shows you the power of that hidden efficiency. I mean, just look at the difference. A faster rate of efficiency doubling doesn't just nudge the curve along. It radically, fundamentally bends it downwards, making progress that might have taken decades achievable in just a few years. This is the real engine room of AI progress.
So we have this engine that is just absolutely hungry for scale. That brings us to our final layer, layer 4, the silicon race. This is where we see the real-world consequences of that demand, right down at the level of the chip itself.
A modernized version of a classic computer science rule, Amdahl's law, really helps us out here. It reframes the whole hardware design problem. Instead of just thinking about parallel versus serial tasks, it asks us to think about the value scalable fraction. That's the percentage of a job where just throwing more compute at it actually produces a better result. And for AI, thanks to the scaling laws, that fraction is huge, and it's getting bigger all the time.
And this creates what the paper calls a race diagram. Look at that curve. As the value scalable part of the work, that S value, moves to the right, the bar for justifying a specialized fixed function chip gets exponentially higher. To be worth it, a special chip can't just be a little better. It has to be radically more efficient than a flexible one, or it's just not worth building.
So the bottom line here is this. The very nature of AI scaling creates this immense economic and engineering pressure away from specialized, single-purpose chips and pushes us towards general, programmable hardware like GPUs. The need to scale is so powerful, it makes flexibility king.
All right, let's pull all 4 of these layers together now into our one unified framework.
And here it is, our 4-layer funnel. At the very top, you've got the absolute limit of computability, where intelligence is just this infinite process of ascent. Inside that, you have the practical boundary of feasibility, a staged climb of what's actually reachable. Driving all the progress within those bounds is the empirical engine of scaling laws, supercharged by that hidden efficiency. And right at the bottom, the architectural consequence, a hardware race that favors programmability.
Now, this isn't just some academic exercise. By understanding that AI progress isn't magic, but this structured, multi-layered phenomenon, we gain a really powerful lens. It helps us make sense of the breakthroughs happening today, and more importantly, it helps us anticipate the challenges and the opportunities of tomorrow.